So we're talking about the laws of thermodynamics. I think I mentioned there's actually 4 laws, but we're really going to be focused on these first 2. The first law of thermodynamics, that is the idea that energy cannot be created nor destroyed. It can only change forms. And then the second law of thermodynamics deals with the quantity we call entropy. Entropy is essentially chaos or unpredictability. And what we find is, at least the prevailing theory associated with this law, is that everything that happens and occurs means that more entropy is being generated somewhere in the universe. So what that means for us, when we're talking about chemical reactions, that means any time you have a process, any kind of reaction, some of the energy associated with that reaction is going to be lost to a more chaotic form of energy called heat. That's the second law working for us. So first law, energy can go to any form. Second law, some of that energy's got to go to heat. Right? So there's 2 more types of energy we might mention here. Your text talks a little bit about work, the ability for a cell to do work. That's really what we need the energy for, is for the cell to do what it needs to do to increase the order within the cell, build larger molecules, to anabolize larger macromolecules. That's going to be work energy. It's going to harness or harvest the chemical energy stored in, a lot of times, glucose to do work, convert that chemical energy to work to do what it needs to do. Heat, again, is energy that the second law dictates it has to be. Anytime you release energy or modify energy or change energy, some of the energy, it's not lost necessarily. It just gets converted into heat. And we can't ever get all of that heat converted back into a useful energy, like a chemical energy in a bond, kinetic energy of a molecule, or work energy to increase the order. All right, so that's kind of how the first and second laws come out. I'm going to post a video, a lecture I do with one of my Intro to Engineering courses, where we talk about energy. I talk a little more in depth than I can talk here about the first and second laws. So I'm going to post that information. Watch that if you're interested. It's completely optional. If you find it helpful for our discussion, please, by all means, watch that. But check the website there and on Canvas, and I'll give you more information about that. Okay. All right, for us, when we're talking about energy associated with chemical reactions, we have what we call the Gibbs free energy. That's this delta G right here. This is the Gibbs free energy. Your text talks a little bit about who Gibbs was. I'm not going to pretend to be an expert there. But the Gibbs free energy, that is the energy associated with a chemical reaction. Now, there's 3 terms there. Let's break those down a little bit. The delta G is what we call the change in free energy, or the Gibbs free energy. Delta H is a term we call enthalpy. Energy of the system is a perfectly good explanation of that. It's not what I would tell my thermodynamics students, but for our purposes, that's a perfectly reasonable explanation of delta H. T delta S. Now, I wanted to talk about the laws of thermo first before we try to introduce this equation. Your text goes in the opposite direction. I wanted to talk about what is entropy a little bit first. The T delta S, that is the change in the entropy. For the S is the entropy. So if I take the temperature which that reaction occurs multiplied by the change in entropy, that shows me how much energy essentially has been lost, if you will, or converted to heat, a more chaotic form. Now, I don't think we're going to do any calculations here. Don't worry about that. We just want to talk about quantitatively what's going on with this equation. Okay, so you have what we call exergonic reactions. That's reactions that release energy. And that means when these happen, you're going to decrease the H, the enthalpy of the system. That's going to result in a decrease in your free energy, your Gibbs free energy. And these equations can occur spontaneously. Doesn't mean they happen readily. It just means they can occur spontaneously if delta G is negative. And we'll pick up there on the next video.